Morning, everyone. So we're going to continue on in this energy option. So far up to this point, we've looked at C1, looking at energy sources. To be a useful energy source, we want to make sure that it's going to provide good quality energy. Hopefully, it didn't take many energy transformations to get it into the form that we want, because we know from the second law of thermodynamics, every time we convert the energy form, we actually lose a lot due to heat. We're always fighting this losing battle here. Today, what we're going to look at here is it's sort of in contrast to the fossil fuels, which were chemical stores of energy in C2. We're going to actually look at nuclear sources of energy. So for nuclear chemistry here, we are focusing on reactions of the nucleus. So we're going to see normal chemical reactions involve valence electrons. The outer shells actually do the colliding and the bonding. In this case here, we're going to look specifically again at those decay reactions, alpha, beta, gamma, and then generalize them a little bit more. There's two generic equations that we look at. One is called fission. Fission means we separate. The other nuclear equation is fusion, which means typically we take lighter things and we kind of sort of glue them together. In both cases, they are useful sources of energy. So by undergoing this reaction, whether it's the breaking in fission or the forming in fusion, it actually does release energy. So just like before, we're going to have a look at the PowerPoint slides just as a quick introduction, and then we're going to look in our textbook for a little more detail. This is section C3 as well as C7. C3 was the standard level stuff, but for higher level, we'll couple it with C7. Starting off with the first big idea here is that if I have a very heavy nuclei, we're going to see that the most stable element on a periodic table for this nuclear context here is actually iron. Anything that's heavier than it could actually undergo these fission reactions, these breaking apart reactions. Eventually, like I mentioned, it's going to be releasing energy. And just the terminology that we're going to use in this section here is undergoing fission allows it to increase the binding energy per nucleon. It allows it to release the energy once we end up forming those daughter nuclei. Any extra energy that I don't need, it's called the binding energy, and it gets released off. We'll qualify some of this, what does it mean for binding energy per nucleon, as we step our way through here. Essentially, one big idea here for binding energy, turns out if I take any old atom, we're going to look at helium as an example later on. Helium we know is made out of 2 neutrons, 2 protons, as well as 2 electrons. From the periodic table, it's already weighted the different isotopes, and it's given me some average mass relative to carbon. If I then took what's called the rest masses of those nuclear particles, if I take the actual mass of a proton, 2 of them, 2 neutrons, and 2 electrons, I add them up, I realize that the total mass, if I sum up the individual Lego pieces, it's actually a little bit higher than once the helium atom itself actually forms, the mass is ever so slightly smaller. We know from mass conservation here this can't be. Even if there's a really small difference, that shouldn't be the case. So what we're going to learn in this section here is some of the mass in forming the actual nucleus, in forming the center. We actually convert some of the matter, some of the mass, we'll call it a mass defect. We'll convert it into what's called binding energy. The binding energy then stabilizes the nuclear core, and then the energy that's released off we can hopefully harness for nuclear energy. So just another closer look at this binding energy per nucleon. When they introduce the term nucleon, they mean particle of the nucleus. So we know the nucleus is specifically protons and neutrons. When we do the example, we're going to start off using electrons, but it is better just to consider just the summed mass of the nucleus, compare it against the individual particles. So just another look at this binding energy here. We know our nuclei is made out of positively charged bits as well as some neutral neutrons. We know positives from Coulomb, they don't like each other. Like charges want to repel away from each other. Why is it then we can manage to squeeze this nucleus into such a tiny space where all the positives really hate each other, all the positives are really pushing away from each other, we're getting to such small atomic distances that the repulsive forces are actually tremendous, and the question here is how come the nucleus itself doesn't actually break apart? We learned from our fundamental forces in physics here. Basically, we have something called the strong nuclear force. If you imagine there's a imaginary set of hands that are constantly squeezing the nucleus together, I know the particles of the nucleus don't really like each other. The protons are constantly trying to push each other away. part of the future for the strong nuclear force, neutrons do help a little bit. Neutrons are neutral particles. Neutrons can act as little spacing molecules. They can separate the protons ever so slightly farther away. Even that small separation is good enough. But again, in this context here, we're going to see neutrons to protons, neutrons to neutrons. They are able to apply a strong nuclear force, and that's actually an attractive force that's constantly trying to keep this nucleus from breaking up due to the electrostatic repulsion. So binding energy here is the energy depending on whether you're looking at energy input or energy output here. In this case here, if I already have formed a nucleus, the binding energy is now the energy, sort of like bond enthalpy. When we're endothermically putting energy in to rip apart a nucleus here, they're defining binding energy here as the energy needed to break up your nucleus back into those individual protons and individual neutrons. I already mentioned here, we're going to see a question of this later on, protons and neutrons, their rest masses, their actual masses, are actually a little bit heavier than once the nucleus actually formed. So in this case here, because we need to generate more mass, it's actually going to put in that energy. The energy gets converted to mass, and it's going to make up that difference, making sure mass is conserved. More so when we do our questions, we actually want to do it the other way. We actually start off with, let's say I have a bunch of free protons and neutrons. I have a bunch of these Lego pieces. I'm going to let them somehow fuse together, somehow combine together as they form a net mass that's tinier than their individual nucleon masses by themselves. That extra energy, also equivalent to binding energy, is ending up released, and that's what we're going to harness for our nuclear source. We're going to specifically, in this case here for binding energy, we're going to look at whether binding energy is high or low. Definitely as we step across the periodic table, we're going to get more protons, more neutrons. To make sure it's fair, we're going to actually qualify and actually calculate here. Sure, we have a sense of what binding energy is, but what we're going to do is we're going to actually divide it by the nuclear particles, by the total number of protons and neutrons, so that we know what's your binding energy per nucleon, and I can do that as a fair comparison over all the different atoms. So they're telling you here, the greater the binding energy, the more the atom sort of stabilizes each other here, the more stable the nucleus is. So using an enthalpy or energy argument here, we would always prefer to go to the case which has the highest binding energy. So this is a graph that we're going to see a couple times here. On the y-axis, we're actually plotting the average binding energy. So that was that net transfer from mass into energy, but we've divided by nucleons, so that way we can make a fair comparison between the different atoms. As you go across here, this could have been just a number of protons here, but because the strong nuclear force there is not just proton and proton repulsion, there's also going to be proton-neutron attraction, neutron-neutron attraction here. They just qualify in terms of total number of nucleons, the protons and neutrons, the particles of the nucleus. I mentioned here we did the per nucleon here. We're used to energy as being measured in units joules or kilojoules here. We're going to see that because we're actually going to punch in the fundamental sizes for the mass, fundamental coulombs for the charge, the order of magnitude is actually going to be fairly tiny. So we're going to see in our textbook section here, it may be more convenient for us to convert into another unit called an electron volt. In fact, here a mega electron volt, a million electron volt, and that way we can get a nicer number here instead of carrying a bunch of times 10 to the negative. What I want to show in this graph here is we talked about here binding energy per nucleon here. The higher up on the chart here, the more stable the atom itself holds together. The highest one here happens to be the iron 56, one of the possible isotopes of iron. And what we're going to see overall when we look at this graph again here is if I relatively am heavier than iron, we notice that sure, I have more protons and more neutrons, but when I do this calculation of how much binding energy is there per nucleon, you notice that it's actually less than iron. So these guys here can very happily break up. We call that a fission reaction. We break up heavy nuclei into smaller daughter isotopes here. And in doing that, in forming the smaller isotopes, as I get closer and closer towards iron, you notice my binding energy actually gets more and more stable, so it's able to release off any extra energy harnessed as nuclear power. Fusion is exactly the opposite here. Fusion, in terms of gluing things together, we generally want to look at things that are tiny. You'll notice there's actually a quite dramatic increase in binding energy at first, but nonetheless here, if I take some of these nuclear particles, these are fairly light, if I end up gluing them together and they slowly form heavier and heavier atoms, as I approach iron, again, I get more binding energy per nuclei, I get more stability the higher up on the chart. Left to its own vices here and using just an energy argument, everything should go towards iron because iron is the most stable out of all the particles. So on this chart here, on the x-axis, we have roughly our smaller nuclei. Those are the ones that get fused together, glued together. And as you go across, larger nuclei. And in both cases, we're trying to approach iron-56. Binding energy here, we're going to see in our textbook section, also is related to the mass defect. The mass defect, again, is the mass loss or the mass change. It's going to be the difference between the mass of the nucleus. We know the nucleus itself, once formed, is made out of protons and neutrons, and we subtract off the mass of all the Lego pieces before it actually ended up forming an element itself. What if we added up just the number of protons that we have and just the neutrons? That difference there is going to be what's converted to binding energy. Here's a general fact here. The nuclei are actually lighter than the sum of their individual nucleons. So once the thing here stabilizes together, once the strong nuclear force has a good hold on this core here, it ends up converting some of that extra mass. It's not going to be by much. We're going to see in some calculations, but that energy gets converted over to mass. Nuclei are lighter than the sum of their individual nucleons. We know conservation mass. Where did that extra mass go? Okay, that mass defect had to do something. In this case here, we're going to harness that energy here. The mass is actually converted to energy that gets released whenever we form a stable nucleus. Or you could ask it the other way. If I have a stable nucleus, I can apply this exact same energy based on energy conservation to rip apart the nucleus, transfer that energy back into mass, and actually make sure mass is conserved. So in this section here, we're going to use Einstein's very famous formula here from special relativity. Energy and mass are sort of two sides of the same coin. They get scaled through speed of light. Essentially, we're saying here not only mass and energy can be interconverted between each other here, but sort of these two are proportional to each other. Later on, if you continue on in chemistry and physics, there is a time that we're actually going to redefine speed of light instead of the 3 times 10 to the 8 that we're going to use in our calculations, making sure everything is in joules and everything nice. If you did go on, you're going to actually see speed of light sometimes as redefined as 1. We're going to when we switch over to our textbook section here, we're going to actually calculate what is the mass defect. We're going to use this MC squared kind of formula and then qualify how much energy is actually being released for some of these nuclear reactions, along with the introduction to those electron volt sort of pictures. I'm going to show you just one last slide here. We're going to get our next lesson here actually looks more specifically into fission, and then we'll do a separate lesson on fusion again. You'll notice that what they've done here is they've plotted for you that exact same graph. Fission, in general, means the splitting of particles. We generally are starting with things that are heavy. If I end up breaking things that are large and heavy into smaller products, you'll notice that on the graph here, we go from having a binding energy per nucleon of about 8. As I start breaking up into smaller and smaller things here, those daughter isotopes are actually more stable than my individual bits, and therefore any extra energy gets radiated away. Whether it is a fission reaction in this picture here, 2 days later when we actually take a look at fusion, it also increases binding energy in both cases, whether the breaking or the gluing together. As we approach iron-56, we end up producing nuclei that are more stable and therefore should be able to release energy. So let's have a look at our textbook and take a look at some more details. So we're going to continue taking a look at the textbook section here for this nuclear part. We're going to look at here C3 to C7 here, specifically looking at nuclear fusion and nuclear fission. Just keep in the back of mind here, fission always means break apart. In this case here, you could imagine I would have heavy things that get separated into smaller daughter isotopes, whereas fusion is sort of the gluing together. This is putting together. This is usually going to be taking things that are tiny nuclei and actually piecing them together. We're going to get into a calculation, actually calculating binding energy a little bit later on as well. And in this case here, we're looking at both fusion and fission, increasing the binding energy per nucleon and therefore releasing energy. Just starting off this section here, just qualifying for you again, what's the difference between the chemical reactions we've seen so far and the nuclear reactions? Pretty much most of the chemistry that we've seen has involved valence electrons. It has involved one particle here. The particles have to collide together. We talked about electrons repelling each other. They slow down and they had to overcome this activation barrier. All of those were chemical reactions because they involved electron rearrangement. Some bonds are forming, some bonds are breaking. The type of nuclear chemistry that we're getting back into for this section here, it involves the nucleus. So we know the nucleus itself are protons and neutrons. They introduce that term again here called the nucleon. atoms, in this case here, when we actually change from, if I end up releasing off an alpha particle or a beta particle, when I actually spit off different numbers of protons, I actually may be a different element on the other side. So whereas when we did our balancing normally, if you were magnesium on one side, you're still magnesium on the other side. For a nuclear reaction, you might be, let's say, uranium on one side here, but you're totally no longer uranium on the other side. What is conserved still? We can't conserve sort of balancing the elements themselves. What is conserved here is actually the nuclear particle. Okay, so nuclear, and we'll get into this a little bit over the next 2 lessons or so. Nuclear particles are conserved. So just because the number of protons aren't necessarily going to be in all the one and same parent isotope anymore, but if I had, let's say, 92 protons for uranium, if I shoot off 2 for an alpha particle, I still have to have 90 somewhere. So we're going to instead use the numbers of nucleon that are actually conserved to actually predict what we actually form out of these reactions. This one here does get into a little bit of background. In fact, protons and neutrons aren't the tiniest subatomic particles. We actually have something called a particle zoo. It could have things like neutrinos, antineutrinos, muons, gluons, things like that. But in this case here, we are going to look specifically at our nuclear particles. Actually, in our section 4, fundamental particles here, it actually gives us, these ones here, you can call them the rest masses or the rest charge. Basically, this is if I could isolate just this one subatomic particle, just a single proton, where we've been saying here, well, the proton is all too tiny here, let's just call it having 1 atomic mass unit. Again, it's best to say no units here, is relative to carbon being 12. That 1 there is actually relative. In fact, here in kilograms, that 1 here is this 1.67 times 10 to the negative 27. Similarly for a neutron is ever so slightly heavier than a proton. So a neutron, let's draw it slightly larger here. Again, the rest mass of the neutron here, you see that not by much, it's still 1.67, but you see it is ever so slightly higher mass. Similarly for electron here, an electron are very tiny in comparison here. The rest mass of electron is this 9.1 number times 10 to the negative 31. So even though it was convenient for us to have, let's make, if I have 1 atom of C12, let's just call it having 12 of these atomic mass units. It was a relative atomic mass units. Again, best case scenario here, you're actually not going to put any unit notation for it. But even though the 1 was convenient, 1 for a proton, 1 for a neutron, in fact, when we go back into SI units, it actually is hiding a lot scarier number. In exactly the same way here, we have sort of these rest charges here. A proton, where we would say, a proton has a full positive 1 charge. Or an electron, even though by mass it's very, very tiny, we usually throw around a number, it's about 2,000 times smaller than the mass of a proton or neutron. In fact, if you look at this is called the fundamental charge or an elementary charge, the charge of an elementary particle like a proton and electron, this does have a full negative 1. So again, in the units that we actually need for coulombs, for the SI units here, the number is a little bit scarier. We just decide to do relative instead, so it's much easier to say, plus 1, plus 2, negative 1, negative 2. Right? There are, just introducing to you, there are more particles than this. Those particles will also have rest masses and differences in charges here. They just introduced one of them for you here. A positron. A positron is essentially everything the same as an electron. We call it an antiparticle, has exactly the same mass, whereas an electron may be an electron with a minus charge. A positron here is actually said to be electron with a positive charge. The charge is implied as a left-hand subscript here, so especially as we get into our standard atomic notation. Let's take a look at an alpha particle. An alpha particle here should be a helium nucleus. It should be a 4-2. We'll get into this in a later lesson. Usually the type of chemistry we're getting is so weird that we normally leave this plus 2 out, but it's okay because it's actually implied over here. If you have 2 protons, I know protons have a plus 1 charge, so I know it's going to be plus 2. Similarly, for an electron, we're going to use as a placeholder. Electrons practically have no mass in terms of this grand scale here. We're going to put a negative 1 just for bookkeeping. It is not an anti-hydrogen, but this one here is an electron, where I would have said an electron is negative 1. Again, I can imply that in the lower left subscript. So that saves me a little bit of writing. I don't necessarily need it in the top right corner. I can read the sign on the bottom left corner. What they say here is if I take these 2 subatomic particles, this positron, this weird antiparticle, I collide it with an electron, both of them are destroyed in a collision. Well, what happens to the mass then, right? They actually physically started off with mass. As they get destroyed, that mass is therefore converted to energy. And that's just sort of introducing to you again, mass and energy are sort of two sides of the same coin, especially with this nuclear context here, mass and energy can be interconverted to each other. So here's our key term here. We called it mass defect. This also gave us our term here, binding energy. So binding energy. Binding energy, or the mass defect, this delta M, is the difference between the nuclear mass. Once the nucleus itself is actually formed, the nuclear mass would be protons and neutrons, and the sum mass of the individual nucleons before the nucleus itself formed. If I count exactly the same number of protons, exactly the same number of neutrons, what if I took just the mass of the protons and just the mass of the neutrons? In that case there, I'm going to find that the individual particles are actually slightly heavier than the nucleus itself. Just like mass has to convert to energy here, that binding energy gets released off. So binding energy is the amount that gets released when the nucleus fused together, or in contrast here, if I end up breaking the nuclei back into nucleons, it's the amount of energy that it would be given off in that case. We will be using E equals mc squared. C, again, is speed of light. You have the constant 3.0 times 10 to the 8, and that's your proportionality factor here. You do need to square it, and therefore make that conversion. Let me actually go to some of these sample questions just to practice, and then we'll come back and finish off this section here. So let's say we were asked the question here, I want you to calculate the binding energy. Calculate the binding energy for helium. Right, so I just chose one helium. I'm going to, and usually when we do units for enthalpy and energy, we say kilojoules per mole. So I'm going to qualify this is the kilojoules per mole that I want. So in this case here, you would start off with the helium. On your periodic table, we know helium is element number 2. It should be a 4.00. The atomic number 2 tells you have 2 protons. The total mass comes from protons and neutrons. That means I also have to have 2 neutrons. Realistically, this helium here should be 2 protons, 2 neutrons, as well as 2 electrons. You're going to see for most of these calculations later on, I actually don't worry about the electrons because I'm just worried about the particles of the nucleus, but I'm just going to show you how this works here. Helium, if I had a little bit more precision on the atomic mass here, this number had to be given to you. So I could read the 4.00, but because we're getting so far into the decimal places here, with this detail here, I'm actually going to write it here, 4.002603. This is the mass of the nuclei. So once the helium atom itself forms, some of the mass has actually been lost. It actually is this 4.002603 atomic mass units. Let's compare this. So this one here is the nuclei. Let's compare it to the individual nucleons. So if I look at the Lego pieces that actually build this up, let's take table number 4 and let's add up how many protons I have, how many neutrons. I could throw in electrons. Those electrons in both cases would get canceled out. I want to end up figuring out what is the total mass that we're getting. So similarly here, let's go 2 protons. 2 protons would be 2 times the rest mass of a proton is this 1.67 number. Since I have it, I'm going to copy that number directly down. 1.672622, you have it on your data booklet. That's currently in kilograms. 2 neutrons, likewise, I have 2 times. A neutron is ever so slightly bigger, 4927 times 10 to the negative 27. I'm going to throw in electrons just for convenience here. Again, usually we ignore that. So in this case here, we're going to have 2 times. The electron's mass here is 9.109383. Lots of calculator work here. Make use of that EXP notation. I'm going to add up all those masses together, and hopefully it should be a little bit heavier than the nucleus itself. So 2 times 1.672622 e negative 27 added to 2 times 1.674927 e negative 27 added to 2 times 9.109383. Do try typing it yourself. I'm getting here the mass. In this case here, we are looking at the atomic mass units as well. This mass here looks like gibberish. It's 6.697 times 10 to the negative 27. These are the actual masses. This is it in kilograms. So this really doesn't really help me, right? I don't know. Well, it's not in the same units. I can't make a comparison here. It would be nice. Sometimes in problems, they actually give you these rest masses in terms of atomic mass units. So sometimes they might give you a neutron is ever so slightly heavier. This number here might be 1.008665 U, or this one here is 1.007265 U. Again, a proton is ever so slightly a little bit lighter, so 65 U, An electron is actually 0.000549 U. So if they gave it to you in U, obviously you can convert it. In this case here, I just did it straight in kilograms. So what I'm going to do is I'm going to convert. Well, what is this actual mass here? Our conversion is actually also on the table. If I have 1 U, what I would call the mass of 1 proton, 1 U is actually equivalent to 1.66 times 10 to the negative 27, and that's also given on your data booklet. So either I convert this one here to atomic mass units, or I convert, because we're going to work towards kilograms anyways, let's just do it this way. So 4.002603, that's a U, and if a U is equivalent to 1.66, I'm going to multiply 1.66 e negative 27, and I'm going to do the comparison here. This is now 6.644 times 10 to the negative 27. Finally, I now have the units in the same the unit, so therefore I can make a comparison. You can try it again. If I were given these numbers here again, the 1.008, 1.007, and the 0.00549, you can try it out here. In terms of U, you should have gotten here 4.032. I'm going to do this as the next calculation, so 2958 U. In both cases here, once you have the same unit, you're going to see the individual particles are ever so slightly a little bit higher than the nuclei itself. Even in kilograms here, this one, not by much, but it's enough to actually allow us to have these, what do you call it, the convert mass over into energy. So let me just write this out in a little more detail here. So mass defect here could actually be this number here. It's the subtraction between the two of those. So this number here, so if we want to find the mass defect, this delta M, this one here that becomes the binding energy, you can either, I'm going to show you both cases, you can either take the equivalent one in atomic mass unit, 4.032958, I minus off 4.002603. That one I did before, it was 0.030355 U. So that is the mass defect. I appear to have lost this mass when I glued these things together. That way is a little bit easier because I'm just having to do this elementary charge conversion just once. Sorry, elementary particle conversion just once. Or just in the case that I did it for you here, you could have also done it here. Well, the nuclei here we had said was 6.697 times 10 to the negative 27. I had already scaled it by this 1.66 conversion. 6.644 times 10 to the negative 27. In both cases, whether you convert it first and then subtract, or subtract and then convert, either way is fine. I'm going to be off by a few decimals here, 6.697 e negative 27. I minus out this answer here, and I'm getting roughly here 5.04 times 10 to the negative 29 kilograms. So you notice it's not by much, right? This is the mass defect. I can't sort of account for this difference here in mass. So that is called the mass defect. Where did the mass go? The mass actually gets converted to binding energy. So once that nucleus itself forms, it has a little bit more stability than the individual nuclei here. If I convert this amount of mass over to energy, here's where we can use Einstein's equation. E is equal to mc squared. So finally we get to use it. I'm going to take this number here. Hopefully you have the unrounded number in your calculator. So 5.04 times 10 to the 29. That one there, I'm going to show you the units. This one here is kilograms. The c is the speed of light, 3 times 10 to the 8 meter per second. All this squared. And I got, previously here, I got 4.54 times 10 to the negative 12. You're going to try to keep all the numbers in your calculator so you don't have any rounding issues. So something in the ballpark of 4.54 times 10 to the negative 12. This number here probably doesn't mean anything to you, right, because that's in joules. In this case here, what we're going to need to do, if this is the joule for a single, so this is the energy released per helium atom. Eventually, I wanted the units recoded in kilojoules per mole, so I'm going to have to divide by 1,000. That's easy to get to kilojoules, but I want the energy for an Avogadro number of this. So let's actually take an Avogadro number, 6.02 10 to the 23. I multiply it by this 4.54 times 10 to the negative 12. You can even go 10 to the negative 15 for kilojoules, divide it. Okay. And this one here would give you, at first I get 2.73 times 10 to the 12. This is joules for every given mole, or better yet here, 2.73 times 10 to the 9 divided by thousands of kilojoules per mole. So that's how they actually calculated binding energy. This is the binding energy for the entire helium nuclei itself. Remember on the graph later what it did is it did average binding energy per nucleon. How do I actually put it on the axis is actually taking this binding energy, 2.73 times 10 to the 9 kilojoules per mole, divided by nuclear particles here is 4. I divide this number here by 4 and I got 6.83 times 10 to the 8 kilojoules per mole. Just before we work through another example of this one here, I'm going to show you a conversion over to electron volt, and then eventually we can get back onto that y-axis unit in terms of electron volt. So I just want to show you sort of one worked out example here, depending on the question. So sometimes we are limited to just looking at a data booklet here. They give us the actual rest masses of the protons and neutrons. You'll notice that I added them up already in kilograms. That sort of bypasses step here on having to do it in atomic mass unit. Nonetheless, you should be able to get this mass defect. There's a difference in mass between the individual Lego pieces and the nuclei when it ends up forming together. And then just a few conversions over. Let's use MC squared here to get it energy, and then let's put the energy unit correct into the kilojoules for mole quantity over to electron volt. That there is your binding energy here. Again, I'm going to work through one more example with you, but let's have a quick pause from there, and we're going to take a look at just some more detail. In this case here, next page over, we have radiation. So radiation, we will see later on a repeat of the alpha, beta, gamma radiation like we said earlier. It's actually interesting here when we actually plot a graph here, they're plotting number of neutrons on the y-axis and number of protons on the x-axis. We're going to find that early on the periodic table, every time you sort of step over, right, we pick up a proton, we pick up a proton, at least for the fairly light elements, the proton number and the neutron number are relatively the same. Helium has 2 protons, 2 neutrons. Lithium has 3 protons, 4 neutrons. Not exactly the same here. What they've actually given you here is a line here. You'll notice for the light elements, what they've done for you is they've actually plotted how many protons versus how many neutrons. So I know in total it gives me the nucleons, but it's comparing how many positive particles do I have in the core relative to the number of neutrons. We have a line here that says if my proton and neutron number stays exactly the same, we should fall along this line. When you actually plot all the elements and you actually dot them, you actually realize, sure, the light elements, they actually fall in this line fairly closely. But as I get higher and higher, about element 20 or so and onwards, 21, 22, and things like that, we'll notice, although I only pick up 1 proton, I just step across by 1, I pick up a few more neutrons. And this is just to show you here, when I am a heavier element, even that stable iron 56 that we said here, 56 protons would have only been here, but iron actually has way more neutrons, and part of the feature of the neutrons is to make sure that there's enough strong nuclear force. As I get too many protons in the core, as I get way too many positives repelling each other, I need to have neutrons that are those spacing molecules that can actually hold my element together. So here what they're saying is if I have a light nuclei, when they sort of follow this proton, neutron, very similar number, the strong force is already enough to counteract the electric repulsion. The strong force is roughly 100 times more powerful than electric. It's blind to charge, so it's going to attract neutron to neutron, neutron to proton. Right? So the strong nuclear force here is a really, well, the name suggests here, it's a very strong attraction, and it's used to overcome, well, when I have too many protons here, let's say a proton and proton is repelling each other here, these protons are hating each other, these protons are pushing away each other, but the strong nuclear force is trying to keep neighbor and neighbor together. So in relatively light nuclei, when I don't have that many protons, I don't need that many neutrons to have enough strong nuclear force. However, as I start getting heavier nuclei, as I start getting more and more protons, the repulsion gets to be a lot more dramatic. This repulsive force here, yes, while there is still going to be a strong nuclear force between these neutrons here, I'm going to need, in this case here I drew 6 protons, I'm going to need not only, let's say 6 neutrons, right, same number of neutrons, I'm going to need maybe, 9 neutrons, 10 neutrons. And basically what's going to happen here is, although the strong nuclear force dollar for dollar, it is stronger, given so many positives are actually repelling each other here, I need way more neutrons as an attractive force. The attractive force here is also, it's a lot closer acting, so only acts on sort of the immediate neighbor. I need these neutrons not only to space out the protons, but to allow for enough attraction, to allow for the protons to be far enough away so that the protons on one side don't manage to repel the protons on the other side. It actually manages to hold together. So long story short there, as we get way too many protons, I need way more neutrons to stabilize them. So what we end up with here is something called the band of stability. We have our stable elements up until uranium. They exist between this sort of, although not exactly the same number of neutrons and protons, they exist somewhere within this band I'm highlighting in purple. What's going to happen then is if I'm at any point here away from it, if during an alpha decay I end up landing way over here, oh, I have way too many protons versus the number of neutrons that I have. If I have way too many protons, we're going to undergo something called alpha radiation. Alpha radiation will end up allowing me to release off some of those protons to actually minimize some of that repulsion. If during another decay here, I turned out to have too many neutrons, so if I end up somewhere over here, right after a decay, whether it be fission or fusion, what I'm going to do, I have so many neutrons here, I don't need so many neutrons, I only have so many protons pulling away from each other, maybe I'm going to interconvert neutrons back into protons, getting back into this band of stability, and that's actually called beta emission. So that's one feature to actually tell you when things will undergo alpha radiation or beta emission. We have that graph again. I mentioned here the average binding energy per nucleon. We're going to do a conversion over to mega electron volt in a second here. I want you to note here, iron 56 is the most stable isotope. So on this sort of binding energy per nucleon scale, we actually get more stability as you go upwards. And whether we are uranium and we're heavier than and we break up, both a fission reaction ends up getting more binding energy, that's going to release energy, or a fusion reaction here, if I have lighter particles and it ends up going to this one here, a fusion reaction will also increase the binding inside the nucleus, any extra energy that gets released off. So both fission and fusion end up as a possible nuclear source for us. In this case here, we just have relatively small nuclei because they're plotting a number of nucleons and relatively larger nuclei, but the goal here is I'm trying to get to iron 56. So when you graph that there, they're showing you, this will be in our next example, helium actually has a binding energy per nucleon than hydrogen. Hydrogen is only down here, whereas helium actually goes up here. We can actually calculate, as I get closer and closer to iron, how much mass defect there is, how much mass has been converted over to energy, and how much energy can I actually harness. So here they actually qualify. These are two terms for today. Nuclear fusion is actually gluing lighter things together. They are currently on the left of iron 56, and they're currently trying to get heavier so that they become iron 56, or nuclear fission, which is the breaking apart. As they break apart, a heavy nuclei wants to reform the iron 56 again. One last comment on units, and then we'll do one more worked example here. An electron volt, just like we saw in the earlier question here, the joule, kilojoule number here, these numbers here were very hard to just sort of keep these powers around. What we can do is we can define a new unit. This is called an electron volt. An electron volt here is a measure of energy, even though it does have that term volt in it, but it's the amount of energy that an electron will have as it travels through a 1 volt difference. So if you imagine I have electric plates here, I have a positive and a negative. Let's say there's a voltage difference between these two here with 1 volt. An electron has a negative charge. The amount of energy that it would need to end up moving this electron through this 1 volt difference is equivalent to an electron volt. So voltage is how much energy you would need per charge as carried. In this case here, an electron is an elementary particle. So I could say relatively it's just -1, or in coulombs you can carry around that scary number of this 1.6 number times 10 to the -19. So let's go through a little bit of the math here. 1 electron volt is trying to traverse this 1 volt gap. I carry a charge of this 1.60, and therefore when I multiply the two of those, I end up rearranging that. I took voltage, I multiplied it by the charge. I now have the amount of energy that I need to do that, or if the electron was freely, in this case here, the electron is just freely going that way here, here's how much energy would have been carried by that electron. So 1 times that number doesn't change the number, it's just 1.60. This is nice because this is already in the scale of 10 to the -19. We also talk about sort of creating per mole of atoms. So what they did here is they took an Avogadro number, they multiplied this energy, and they get 96 kilojoules per mole. And you notice here, in this case here, I derived 1 electron volt is equivalent to 96 kilojoules per mole. So earlier when I had gotten kilojoules per mole, I could have divided over 96. I get electron volt. That's similar in magnitude to reaction enthalpies, like delta H's that we did in chapter 5, and that actually gets us closer to this unit here, electron volt, although they actually have mega electron volt. I'll do that last detail here in this next example. So, just wanted to introduce to you some of this nuclear chemistry stuff. Let's just do one more worked example through. I want you to calculate how much energy is actually being released here. So, calculate the energy released for the nuclear reaction. And just to give you one here, this is going to be taking a hydrogen. This is actually called deuterium. It's the isotope that actually weighs 2. I'm going to fuse it together with a hydrogen 3, which is a tritium. I'm going to fuse it together. This is really weird chemistry. I'm actually a helium on the side here. And the question is, how many neutrons would I need to balance? So earlier I had said nuclear chemistry is weird. I may be one element on one side, a totally different element on the other side. At least the number of core particles has to stay the same. So for example, for a helium, I know a helium has 2 protons. I know it has 4. Well, I had 1 proton, 1 proton. Oh, instead of being in 2 different isotopes, they actually get glued together. They're one atom here, just helium. I had 1 neutron, right? So total mass of 2. I had 2 neutrons here. I have 3 neutrons total, but here I only have 2 neutrons. Or you could say I have a mass number 2 plus 3 is 5. I only have 4 here. Well, then I can predict for you how many neutrons actually get radiated away. I'm going to give you this time, instead of earlier, we weren't given the atomic mass unit equivalent. We had to use the table 4. What I'm going to do here is I'm going to actually give you the atomic mass units, just so that you get some variety here. 2.01. These would have to be given to you because this is a lot more detail than even our periodic table would give us. So these are the equivalent atomic mass units. Earlier you saw what I did is I actually took, well, the total mass of the helium. The total mass of the helium would include these electrons here. Well, if the mass of the electrons here and the mass of the electrons here, those are unchanged, I could actually sort of ignore these neutrons, ignore these electrons. This mass here might be a little bit smaller. If I don't add the electron, that mass would be a little smaller as well. At least the mass defect between the two of them would be the same. So in this case here, I think they're including the electrons as well. So let's just go through here. Let's figure out here the mass defect should be the total mass of the products minus the total mass of the reactants. I'm not having to actually break apart the rest masses again. I'm just going to just do a general comparison. How does the total mass at the end compare to the total mass at the beginning? So in this case here, I'm going to take the 4.002602, add 1.008665. In total, I get a mass of 5.011267. Try to keep all your decimals here. Add the reactants here, 2.014102. Double check my math, 016049. I'm getting here 5.030151. Again, I want to emphasize here, mass defect isn't a whole lot, but you notice there actually is a difference here. So let's just type these numbers in. If I took the 5.011267, I minus off the 5.03051, I have a loss in mass. How much mass did I lose? I'm getting here, I have lost a mass of 0.018884. I'm not worried about this negative here because I know mass lost was converted to energy. It's more so the size of it, how much mass was actually conserved that I'm interested in. So for here, this one here is currently atomic mass units. We're going to need the conversion. One atomic mass unit is 1.66 times 10 to the negative 27. You'll notice again here, this is on your data booklet, you'll notice that is very close to the mass of a proton and neutron, but a proton and neutron are ever so slightly a little bit higher mass than an atomic mass unit, so just be careful of that. So we do this conversion here, I multiply this number, 1.66 e negative 27, in kilograms, this number would be 3.13 times 10 to the negative 29, this one here is kilograms. We can use Einstein's equation, so special relativity, E is equal to mc squared. Let's take this 3.13. I'm going to keep the whole number in your calculator, times it by 3 times 10 to the 8, but squared. So let's rescale it through speed of light, times 3e8 twice, and I'm getting here 2.82 times 10 to the negative 12. I'm still keeping the entire number in my calculator. That one comes out as the SI unit for joules. I do want to convert this to kilojoules. So in this case here, divided by 1,000, it would be 10 to the negative 9. Is that correct? No, sorry, 10 to the negative 15. Actually, let's just leave it in joules for now. Okay, so we have that joules here. That's the energy per. So this is the per reaction. Remember, we want sort of per mole. So what I'm going to do is I'm going to scale it up by Avogadro's number. Times 6.02 times 10 to the 23. So that way, if I run a mole, every time you run this statement, I actually get 1.70 times 10 to the 12. That's now going to be joules per mole. And here, similarly, we could have done that earlier. We could have, earlier I'd said this one is 10 to the negative 15 kilojoules, or you could do the divide 1,000 at this point here. This is now equivalent to 10 to the 9 kilojoules per mole. That's where we left it off last time. And now we had this conversion. 1 electron volt was equal to, I believe the number was 96 kilojoules per mole. So I can punch it through one last conversion here. I have this many kilojoules. I'm going to divide, right? Use this conversion over. So use this conversion here to put it back into an electron volt unit for us. Divide it by 96. I get the number here 1.77. Oops, back to my pen. 1.77 times 10 to the, I'm getting 7. That's going to be an electron volt, and that's why it's going to be mega electron volt. So if I go a million volt, 1 mega electron volt is 10 to the 6 electron volt. We have 17.7 mega electron volts. So at least I wanted to show you first another example of converting mass. Any difference in mass here was converted over to energy. I want to show you one that you can actually subtract through with atomic mass units. You convert to kilograms, do the MC squared to get it to joules, multiply Avogadro because it has to be per mole. Make sure you have kilojoules, and then I can do this conversion back to electron volt, back to mega electron volt. Now we're in a very small context, like 17.7, and now I could hypothetically put it back onto a graph like this. This one here is mega electron volts here. The one last step here I'm not going to do with you here is they also did per nucleon. That was when I was just adding up just individual particles. I divide out how many total protons and neutrons. In this case here, we're doing a complete sort of a nuclear equation here. There is no sort of nucleon to divide by. So I'm just going to leave my answer here as 17.7. Right? So have a look over some of your questions here. Probably the most important thing is make sure you keep all your decimals in the calculator. So therefore, you don't accumulate any rounding errors. Thanks, guys. If you have any questions, just let me know.